Okay, so I'm going to talk a little bit about front ends. I know some of you already know about front ends. Not all of you are necessarily interested in them, but it's a really interesting area in YT development. And we'll talk about what they do, why they do it, and how you could, in principle, write one. The idea is that with building a front end, front load, the work on being able to access your data multiple times, right? So there are also things that you can do in a front end that can help to optimize data access and data usage. I'm going to show some of those things, and I'm also going to do a little bit of a demonstration why those things are useful. But there's a huge caveat in this, in that optimizing this stuff early is not necessarily the right thing to do. So if you've already got a performant front end, you don't necessarily need to optimize it. Okay, but I'm going to show you the ways that we would do that and places that we have. Okay. So front ends, and this is insulting to all the other types, but there are basically 4 classes of front end. We have grid-based front ends, octree front ends, which are not a special case of grid, I'm told. Particle front ends, and I put them on the right in a position of honor, and then other front ends. So other refers to things like unstructured mesh, and then things that don't totally fit anywhere. They tend to have differences in their index objects, and there are some things that are not supported in all types of front ends. Specifically, unstructured mesh don't all support, as Chris mentioned yesterday, don't support chunking. Probably wondering what chunking is. I mentioned it earlier, but chunking is going to come up in this. The way that front ends work is they are designed to be the layer that regularizes the data that goes into YT. They also provide output-specific information about different relevant components of your data set, of your simulation, of whatever. When we write a front end, we write a data set object, which is generally quite lightweight. Not always, but generally. And then for that data set object, we write an indexer, an IO handler, and something that manages fields. Generally, the field info object is not the most challenging part of writing a front end. It tends to be where we specify things like aliases. And so I'm going to show you the field info part first, and then we'll talk about the indexer and the IO. Look, Evan, you look like you're going to catch it. No, leave it alone. So a front end, formally speaking, lives inside our YT-frontends directory. And typically, we have all these different subdirectories. Now, yesterday, a couple times it got mentioned that you can externally create these, and that's true. And we, at one point, had a front-end template. Is that still a viable concern, Chris?
I think it probably would still run. I don't know what it's giving.
Yeah, it had some shortcomings, specifically in that it was designed for grid-based systems. So if you were to browse through any one of these front-end directories, and let's take a look at, moving way more than I expected. Let's take a look at, let's say, Enzo's a bad example because it has a lot of special cases. Let's take a look at the Tipsy front end. Inside the Tipsy directory, we have a tests subdirectory, which I'll go over. We have an API.py. We have data structures, definitions, fields, and IO. Definitions is often empty. Here for Tipsy, it's not, but it is frequently empty. Definitions is not a rigorously required component of your front end. It's where you can put things that that may need to be externally versioned, but in general, it's actually not used that much. It just felt like a good idea at the time. Like that song seemed like a good idea at the time. Data structures is where your various different objects that implement indexing and reading of files, or sorry, reading of parameter files live. IO is where your IO handler lives. And fields is where your field handler lives. The field handler, again, is probably the most straightforward item to develop. Let me see if I can zoom this in without using too much real estate. The way a field info handler works is it defines fields that exist on disk, and then it provides a mapping between those fields and fields that YT knows about. So let's take a look, not tipsy anymore. Let's look at the Enzo fields. So here's an Enzo field info. It defines cooling time. That's the file name, the field name you might expect on disk. It tells you the units that it should be converted to, and it tells you the units that you would expect it to be in. Oh, I'm sorry. No, it tells you the units that it is on disk. And then it tells you anything that it should be aliased to. So let's take a second to talk about what aliasing is. If we have ds equals load sample isolated galaxy, ds.fields.ds.index, I'll create it. If I do ds.r gas density, that is an alias to ds.r Enzo capital D density. Note that they are in different units because the internal fields get converted into whatever your unit base is, but they are the same field, just with a minor conversion factor applied. So that happens here. We construct, and let's see, it's right here. We specify the field on disk density, and then we have a field info tuple here that specifies the units that it's on disk, whatever it should be called internal to YT. And then this, I think, is the display name. Is that right? It tends to be none. Okay. Promised myself I wouldn't do this. There's a lot of history wrapped up in this. It's a little brittle, but basically what you do is you fill out a field info container with the attribute known other fields. It has to be a tuple of tuples. The second element is also a tuple. The second element of that is a list. It's a little Alice in Wonderlandy, right? Anyway, this is what it gets aliased to internal to YT. This is what it is on disk. These are the units. And then you can put nice display fields. If I go back to Tipsy, I think there might be some display names. Nope, they're not. But here, for instance, u.fb gets aliased, or gets aliased. Oh, that's an auxiliary particle field because that's the name of the field that's the name of the field file. Wow, not going well for me, is it? Take a look at Gadget. Okay, so that's the basic gist of it. Field info tells you what to expect on disk, what to get in memory. Okay. The more fun stuff, don't save, no. More fun stuff is when we start looking at the data structures. So Subsets of the data object or sub attributes of the data object are the indexer, the IO handler, and then they have supporting objects associated with them. So for a grid data set, the indexer is a subclass of the grid geometry indexer. For octree, it's a subset of the octree geometry indexer. And for particles, subset or subclass of the particle indexer class. Each one of these has its own set of supporting objects. So for a grid data set, there actually are grid objects that are associated with it. For an octree, there are, it assumes that there are a forest of octrees, and so there are different files associated with it. For particles, it has sub-chunks inside files. So like if you've got enormous files, it'll cut them up into 64 cubed or 128 cubed or something like that. The indexer is responsible for knowing what can be found where and how to sub-chunk the data. So it's responsible for knowing that this geometric location maps to these files. And that's about it, but its responsibility shows up in multiple ways. It also has to know how to divide up the work for reading data off of disk. And it has to detect which fields are in the files. This is a more complex process than I would like because some data formats, like especially grid-based ones, don't have every field in every file. And so it gets a little bit confusing. You have to do a reduction. But the basic gist is, once you set up a selector, the indexer calls the IO handler with those sub-objects that intersect with the selector. And then the IO handler reads arrays of data from those individual files, applies the selector to them, and then concatenates and returns to the data object. So more specifically, what that means is when I do ds.sphere center 0.1 unitary, and then I were to do something like min density, this object, the sphere, has associated with it a selector object. That selector object then gets provided to ds.index inside read fluid fields. Read fluid fields figures out which grids and thus which files intersect with that selector. And then it passes each one over to my IO handler. The IO handler accepts that information, reads the HDF5 from dataset, asks the selector, which of these do you care about, and throws everything else away. And then it moves on to the next one. If we look at I'm not making this sound easier. Organizational skills, am I? Am I recording? Essentially, with these, there are only a couple objects that are things that need to be implemented. So if you wanted to write a new front end, you start with a skeleton that lives in the repository. You implement read fluid field. You implement read particle selection, and you implement the index operation. So my thought was, why don't we try doing this for a particle data set? Demonstrate how it's done. But then I saw that it was 3:20, that I only have 10 minutes left. What do we think?
I think you can keep going. because
Awesome.
We're just gonna brainstorm stuff.
We
Okay,
didn't need to hear the last part of that. It's like something it's collected from my child.
Tina is safer to that, so. Go ahead. Okay,
Keep going, development stuff. Talked about submitting an pull request for review.
oh, you're right.
Do that first.
Yeah, why don't you actually talk about that for a minute? Yeah. You don't have to plug in, just come up and talk. I'm just gonna take a little
Oh, yeah.
break before you do that.
Can you pull up GitHub? It's.
Feel free.
Okay, so quick aside, before we keep going with the front end. So I just wanted to mention what happens when you are developing YT, you make a change, or how you actually start making a change and then push it up to GitHub. So let's say you have found something in YT you want to fix, bug fix, typo fix, new feature, whatever it is. You already have your fork locally, you have your development environment. Before you start making the change, first thing you do, you create a new branch to make that change on. You make sure that you are not on your main branch. Generally, much better practice to make changes on branches that are not the main branch. You make all your changes locally.
You'll get bounced if you do it, right?
I don't know, do we have checks for that? I don't think we do.
Don't we have a linter that stops you from counting on one?
Yes, but you.
True, yeah.
Right. Which occasionally happens.
Oh, and I forgot to say, you have to pre-commit install.
Cool, okay, so you've done that, you've made all your changes, you're ready to actually push it up and contribute it back to YT. You do that by pushing your branch up to GitHub. Usually when you do that, you'll get a message saying, do you want to create a pull request? You can click that link that you get, and it'll take you to pull request draft page. I think if you do this with GH, there's probably a way to just create the pull request. I don't actually use GH, so I'm that. Easy enough. And so what that will do is create a new pull request, which looks like this in GitHub. So what you do, you write a little summary of what you've done, kind of describe things. There is a checklist that pops up. We use it sometimes, depending on what the changes are. And a number of things will happen. So first off, as soon as you hit submit pull request, as a new contributor, when you hit submit pull request, it creates the pull request, and then one of the maintainers has to go and click a button to run all the automated checks that run. But if you scroll down to the bottom, these are all the automated tests that and mainly tests that run when you submit code changes. So these are all mostly run through GitHub Actions. GitHub will check out this branch and then install your branch and then run all the tests that we have in place. Things are a little bit funny right now because one of our servers is having a hard time. So we have a test suite that runs some tests that require larger data sets. So it's a persistent server where those tests run. So these are not running right now. They're just kind of stalling forever, but hopefully we'll have that fixed soon. So one thing, if you did not install pre-commit, most likely you'll commit something that fails the pre-commit checks. And so this test will probably fail for you, and it'll give you a list of what went wrong. You can go change those, push up things, or you can use the bot to fix it. We've talked about too much. But anyway, when you submit a pull request, we'll all get notifications about it. Over some length of undetermined time, we will look at those changes and write reviews. So this is what the review page looks like when you click on it. And if you're reading through here, you can, comment on individual lines, write comments, feedback, and then so there will be some back and forth with developers. And once it's ready and approved, we hit merge and some other stuff happens. But yeah.
But you don't have to be a member of the YT organization to review a pull request. So if you want to help, that's also one way to contribute. You can review pull requests, not even have to submit fixes or anything. That's also helpful.
Well, I mean,
if you approve a pull request without being a member, you will give it a nice little check, but it won't be green. So it won't allow a maintainer to merge the request, but having a first or second opinion from an outsider is also something valuable.
It's a good way to get involved.
I'll try it.
Other questions about this process? Happy with that little short overview? That's all I had to say about it, but. Oh, the other thing, you can also ping us all on Slack if you have questions about this. We can help you with that problem.
Okay. What I'm gonna do is first, we're going to make a data set. It's going to be in a weird format. Okay. We'll do np.random.normal size equals 64 cube. That'll be X and Z. Okay. And actually, I'm going to do this a couple times. For position in and I'm going to write this all to disk. I'm going to write it in a funny way. Okay. So we'll say np.toFile. And here, let me give this I position in rate. np.toFile, does that take the name first and then the array? I wanted in that. All right, you know what I'm going to do? I'm going to store these in like a weird format. Big endian F8. Big endian normal now. Just made it big or little nowadays. It's little, isn't it? Open it. I'm going to say f.write ex bytes f.write py 2 bytes f.write pz.2 bytes. So we've just got a whole bunch of particle data. Okay. So this is not in a format that we've seen before. It's just particle data. So we want to make a new front end that implements a reader for this. Particle data sets are one of the more straightforward ways to do this. So we'll go to Frontends. I'm going to go ahead and make a new folder. And I'm going to call it my special data. And then inside that folder, let's grab the tipsy data structure. There are multiple different supporting files, as I mentioned. And for particles, typically those multiple supporting files are what are called files. They're subclasses of the particle file class. The particle file class expects there to be a number of different attributes associated with it, including offsets as well as information about the about where those offsets are. So we're going to go ahead and here inside my special data, is that what I called it? What did I call it? My special data. We're going to create a new data structures.py. I'm going to allow a little bit of Copilot here as long as nobody is anyone recording. And I'm going to class my special data file, and I'm going to subclass particle file. Let's see, is it going to do it? There we go. Now let's sketch out the rest of it. What the hell did happen?
Particle file is already an established class.
Yes. And I'm actually going to go ahead and, largely speaking, copy most of this over. First, I'm going to sketch that out, my special data set under SPH data set. See what it does. Nope, wrong. Oh, it's getting a lot wrong. Oh no, that I want. Okay. File class, we'll do none for now. We'll come back to that in a moment. Oh, actually, no, file class, we do my special data file. And so there are different attributes that are specified here inside things like an SPH data set. So for this, my special data set, SPH data set, we specify an index class. That'll come from SPH particle index. We specify a field info class that will need to be specified. We'll call that for now my special field info. We have a particle mass name. That's not going to matter. We have a particle coordinates name. Also not going to matter. We have SPH p types and header spec. We're going to go ahead and get rid of most of this because at this point, it's a little bit free form. What we need to do is we need to be able to load the file and it needs to instantiate things. But for the most part, many of these things actually are managed by the base class. So let's get rid of almost all of this. We'll do bounding box equals bounding box. But we'll get rid of stuff like field D types and whatnot. I'm going to chosen tipsy. He has a lot of complicated things in it. But almost all of this we get to keep. For the parameter file, we're going to get rid of that. We don't have a parameter file. We just allow our dimensionality, our refined by parameters. And get rid of the rest of this too. We'll make it periodic.
So the tipsy file has a few like things right at the top that can go in there.
That's right.
So is that you just forgetting about those?
I'm ignoring those because I'm not doing tipsy.
Right.
Yeah. And we'll say that it's a non-cosmological simulation. Now, for my case, I'm going to set the file count to 3. I'm going to set the parameter file name equal to, doesn't matter. It's not going to use it. And then we'll allow these other things to happen. We'll say that our mass unit is msun, length unit, kilometers. at a time unit. The last important thing that you need to do for this is you need to have a class method that's called isValid. That class method has to return true on a file name. In this case, we will return whether or not that file name dot ends with, what did we call it? My data. My dat. And I think there are a couple other imports that I need to get. Grab those. Okay. From dot fields, import my special field info. Now let's create a field info handler. Copy this over as well. We'll say pass for now. Last thing we're going to do is we're going to create an API file. We will eventually come back to the IO handler. Okay. So the way that this now gets set up is when it gets imported or when it gets instantiated, creates this SPH data set. It knows how to index that data because it knows how to read from a data file. And now we have to implement our actual IO. Is its own chunk size set up? I believe the only thing that you actually need to implement is read particle coordinates. Yes. When I wrote down all my notes about how easy this was to do. Copilot. Oh, wow, look at that. I don't think we need that though. No, none of that is relevant. The hell? We're going to implement read particle coordinates. And this functions a little differently than you might expect. I'm going to leave this in here in case we need to do something other than just call the super. The way particle coordinates get read in is you get what's called a chunk iterator. Those have data files in them. They have field offsets for different fields. and they have information about the total number of particles in them. Now, for our purposes, total number of particles is always the same. Total particles equals 64 cubed. Field offsets. Say particle position X is at 0. Particle position Y is at 64 cubed times 4. Is it times 4 or is it times 8? Nope, times 8. Sixty-four cubed times 8 plus 64 cubed times 8. And then that's it. So this tells us where each field can be found, total number of particles in the file. Now in our IO handler, for each data file in our chunks, we get the total number of particles. It'll always be the same. Open the file name for that data file. And this part gets a little tricky, but essentially we order it so that it doesn't have to seek around. And then it reads until it fills up the chunk. Yeah. There's like irreducible complexity here that I'm really running up against. You're nodding knowingly, Chris. Yeah, we tried really hard to make this better, right? You did, especially with the Dask work. So we don't have any SPH in our item. So instead, what we'll do, it sorts our particle file by the offset so that it reads them in order. It'll always have the same particle type. And then here's the key part. It reads in subchunks. So that way it only ever reads up to whatever that chunk size is, rather than reading the entire file all at once. And then it yields. It yields back the name of the particle type, data that it read from disk and particle coordinates, and the smoothing length. This constructs the index. You can also read our particle fields, and this is what Copilot thinks we should do there. And here, it's essentially the same operation. Once we've implemented these two functions, and I'm not going to muddle through it just now because I don't want to do that to you. But once you've implemented these two functions, which can be implemented, the particle handler system itself will then know how to read each individual particle field, particle type, and it will index them for you. So developing a front end is largely all that it tends to require is developing a couple IO routines and a couple items in the data structures file, but many of these things are already done for you. So there's a lot of copy and paste that can be done. Additionally, this is only for if you've graduated beyond being able to do function calls. So for instance, here, this sorts based on the type of particles so that it gets them all in the right order. That's not necessarily something you would need to do. Okay, I'm going to stop there because I can read the room. Front ends don't have to be the worst. Okay. And I think that it's also something that we have tried to improve in the past, and it hasn't always worked out. And part of the reason for that is that we want to optimize for IO and things like that, which adds complexity in. But another part of it is that the work on doing a front end is generally pretty front loaded. So once you've got it done, in general, it doesn't need to be redone. And that changes sort of the incentive structure. Okay, I'm gonna stop recording. You can all forget that this ever happened.